University in Johannesburg, South Africa. And right now I'm visiting the Max Planck Institute for Software Systems here in Saarbrücken, Germany. So today I will give you a talk about X coordinates of solutions of Pell equations in various sequences. I gave this talk before where I didn't have as many results. So some of these slides have been recycled. I'm sure if you've seen them somewhere else, but there will be new elements in this talk. So let's see what is a Pell equation. I start with a positive integer bigger than 1. It shouldn't be a square. And then I look at the equation labeled 1. And the aim is to find solutions in positive integers x and y. D is fixed. So the left-hand side is x squared minus dy squared equal plus minus 1. You see, if d is a square, then the left-hand side would factor into two linear things. The product is plus minus 1. This gives you a few possibilities. So if d is a square, 1 will not have solutions. But if d is not a square, at least when the right-hand side is positive 1, it always has a solution. That's a theorem. Sometimes for certain d's, it has a solution with negative 1. Once you have a solution, you can construct other ones. And the way you do it, you start with the smallest positive integer solution. Don't be confused by the word smallest, because x and y are related. So the smallest solution, you can think of it the solution with the smallest x, or the solution with the smallest y. And say that that is x1, y1. Construct the element x1 plus root dy1. That's a quadratic number. And raise that to the nth power. And when you raise that to the nth power and you use binomial coefficients and so on, you're going to get some integer plus root d times some other integer. Well, it turns out that that integer, you can denote it xn, and that other integer coefficient of root d, you can denote it yn. And xn and yn satisfy equation 1. And there is a theorem saying that all the solutions are obtainable in that way. So the only thing you have to do is to find the minimal solution. And the minimal solution is related to the continued fraction of square root of d and so on, but we won't go in that way. So my problem would be the following. Take u to be your favorite set of positive integers. My question is, what can I say about the numbers d such that the x coordinate of the Pell equation corresponding to d, x sub n, lands inside u for some n? Of course, you would want u to be some thin set of numbers. If you take u to be all the positive integers, then this is not much of a question because all the xn's are going to be there. You can take more interesting subsets like maybe Fibonacci numbers or squares and so on. But if one formulates and I get a positive integer, which I can write as d times the square for some square-free integer d. And then I just shuffle these two guys around, and I have x squared minus dv squared equal negative 1. So u must be the nth solution for some d. So in this way, the problem is trivial. And if u is bigger than 1, you can play the same game with u squared minus 1 equal dv squared. Well, so the first attempt was not very successful. Let's try a second attempt. The second attempt would be, well, let's take again our set u, but let's ask of more members of the sequence xn to be in u. So let's ask for at least 2 different values of n. So now I'm searching for those positive integers d, such that if I take the Pell equation corresponding to d, the set u contains at least 2 of the x coordinates. Actually, in this form, I think maybe the first time it was studied by a mathematician called Wilhelm Lundgren. What Lundgren did, he took u to be the set of squares. And he asked, when can xn be a square? And he proved that if xn is equal to a square, then always n, the index, is either 1 or 2. So it either comes from the minimal solution or from the second solution. And interestingly enough, d equals 1790 is the only positive integer with the property that both the first and the second x's are squares. So in that sense, this question for squares was studied by Lundgren. Our first result, I think this started sometime in 2014. It was a SIMPA school in Benin, organized by Alain Togbe. And the usual suspects were there, some of them friends of India, like Michel Waldschmidt and Francesco Papalardi and so on. And Alain had some students, so he said, let's work on some problem. So this problem was motivated by the following example. Let me go on the next page. Look at this number, 99 square minus 1. Write it as in school, 99 minus 1 times 99 plus 1. 99 minus 1 is 98, which is 2 times 49, and 49 is a square, and 100 is a square. So this whole thing is twice times the square. Now put twice times the square in that side and move the 1 here. What have you obtained? You obtain 99 square minus twice times the square equal to 1. This means that 99 is some x-coordinate of the Pell equation corresponding to 2, and it's a pretty number in base 10 because it's just one repeated digit, 99. Well, let's do it in general. These repeated digits, they have names. They are called rep digits in base 10. What a rep digit is, it's a number like the 99 from the previous slide. It consists of some digit between 1 and 9, which repeats itself m times. The decimal representation of the number is therefore m times, and if you do the algebra, this is a times 10 to the m minus 1 plus 10 to the m minus 2 plus down to 1, which ends up being a times 10 to the m minus 1 over 9. So here's a result with Apollinaire and Alain Taubé. We prove that if you take xn, yn to be the nth solution of the Diophantine equation x squared minus dy squared equal positive 1, then this equation, x sub n being a rep digit, has at most one solution, except if d is equal to 2, for which it has two solutions, the first one and the third one, and d equal to 3, for which it has two solutions, which is the first one and the second one. What I showed you on the previous slide with 99 is the third solution corresponding for d equal to 2. It also has the first solution because d equal to 2 is small. So the smallest solution is 3 square minus 2 times 2 square equal to 1. And 3, of course, has only one digit. Therefore, it qualifies in being a rep digit. There is no second digit different than it to contradict it. So this was our first result on the topic, and here's a picture of Apollinaire. So I'll show you a lot of pictures of my co-authors. I'll also show you a picture of Alain later. Then once you open this can of worms, then you can say, well, let's put other sequences in there. One of my favorite sequences is the sequence of Fibonacci numbers. It starts with 1 and 1, and then every subsequent term is the sum of the two preceding ones. So you start with 1, 1, the next one is 1 plus 1, 2, the next one is 2 plus 1, 3, and so on. So we asked ourselves, what about the x-coordinate being a Fibonacci number? And the same question, what are the d's such that 2 of the x-coordinates of this Pell equation are Fibonacci numbers? And we showed that, again, d equal to 2 is the only bad guy in some sense. Here we also allow the sign -1. If you allow the sign -1 for d equal to 2, the first solution is 1, 1, because 1 square minus 2 times 1 square equals -1. And 1 is a Fibonacci number even in two different ways. And then you have another Fibonacci number there, which is 3. 3 square minus 2 times 2 square equals 1. And 3 is the fourth Fibonacci number. All these problems can be reformulated in the way I'm writing it down here. Namely, what you do, you take the Fibonacci number f sub n square, and you subtract or add 1 to it, and you multiply it with another Fibonacci number square plus minus 1, and you ask, when is this a square? Well, there's trivial solutions to it. For example, fn equal fm, and the signs are the same. Or there's another trivial solution where one of the numbers is 1, and then you're subtracting 1. In this case, you get 0, which is a perfect square. But then you ask, what about non-trivial solutions? A non-trivial solution, this is the only non-trivial solution. By non-trivial solution, I mean, for example, you take 1 square and you add 1 to it, and then you take 3 square and you subtract 1 from it, and you get 2 times 8 is equal to 16, which is a square. And this game, you can play it for every set. So if you're looking in the set U, you can look at a square plus minus 1 times another square plus minus 1, where both things that you take the squares of come from your favorite set of integers, and you ask, when is this a perfect square? All right. Now you can do variations with rep digits in an arbitrary base. Let's take a base g greater or equal to 2, which is an integer. Let's take a rep digit in base g, which is just the digit between 1 and g minus 1. and it repeats itself m times, so it looks like a times g to the m minus 1 over g minus 1. And with the student of mine at that time, Bernadette Fay, we looked at the result that we proved with Apollinaire and Alain, but we looked for it in all rep digits in the base G. And we proved that if there's two x's, which are both rep digits in base G, then D is bounded. And we even have this bound. This bound is untenable. If you have done any computations at all, you know that you cannot go to x of 10 to the 10 to the fifth. You can probably go to 10 to the 100, which is going to be the x of maybe 200, maybe x of even 1,000 you can probably go, but x to 10 to 1,000, there you cannot go. It's too bad. And I'll come back to this later. This is Mrs. Fay at some conference or summer school. Now she's called Mrs. Fay Fall. We can do variations with Fibonacci numbers. The equation that I showed you with plus minus 1 on the right-hand side, you can play the same game with the equation with plus minus 4 in the right-hand side. This is also called the Pell equation. Like the one with plus minus 1, it always has solutions. Actually, some trivial family of solutions, you start with the one with plus minus 1 and you beef up x and y. You multiply them by 2. When you square, then you get to plus minus 4 in the right-hand side. But it turns out that sometimes this equation, equation number 3, has a bit more solutions than the ones that come from the Pell equation with plus minus 1 when you multiply both coordinates by 2. It has something to do with the unit in quadratic fields when D is congruent to 1 mod 4. This is a result obtained with Bir-Kafle and Alain Togbe, that if we look at Fibonacci numbers starting with at least 3, so at least f sub 4, f sub 5, and so on, then this equation has at most one solution, has at most one x with the property that it is a Fibonacci number with index at least 4. And if you allow small Fibonacci numbers in the game, you get a couple of exceptions, like d equal 2 and 5. And this is Bir-Kafle. He is a colleague of Alain Togbe. They are both based at the University of, Purdue, some side campus in the north of Indiana, not the main campus in Lafayette. Let's look at the proof so far. So this is what we were coming up with at that time, and then it kind of got improved over years. So the way we're starting a bit, let's do the Fibonacci case. I start with x squared minus dy squared equal 1. Suppose that the nth coordinate is fn. And suppose that, that n is even. So this index, the index of the x coordinate is even. Then there are some formulas that relate those coordinates. Once you know that they exist, it's easy to prove. So how would you get a relation between x sub n and x sub n over 2? Well, you'll take x sub n over 2, which comes from x1 plus root dy1 everything to power n over 2, and you would square that relation, and you would get a relation for x sub n. And if you interpret what you're doing, that's the formula that you get. This can be rephrased in terms of Chebyshev polynomials and so on. So in particular, I'm looking at Fibonacci numbers, which are of the form twice times the square minus 1. Well, it turns out that the Fibonacci numbers, they naturally participate in some Pell type equation. So you take the Luka companion of the Fibonacci sequence, which has the same recurrence as the Fibonacci sequence, except that instead of starting with 0, 1, it starts with 2, 1, if you start from 0. And then you assume that f sub m is 2x squared minus 1. You stick 2x squared minus 1 inside here. You move the 5fm squared to the other side, and you get that if you denote L sub m by y, you get that y squared is this polynomial of degree 4. It turns out that this polynomial of degree 4 has only simple roots. And then there's the theorem of Ziegel saying that if you have a Diophantine equation of the type y squared equal f of x, where f is a polynomial with simple roots and degree at least 3, then it has only finitely many integer solutions. And there are ways of computing these integer solutions by relating them, in the case of polynomials of small degree, by integer points on elliptic curves, and there's programs that do that like Magma and so on. So you find those integer points, then you go back to the integer points, you check which one of them was a Fibonacci number, and you check for the values of d that would come up from some integer point and gives a few d. So we find all the solutions n in this way. So this was for the case when one of the coordinates was even. And notice that this proves more. This proves everything if x sub n is a Fibonacci number when n is even. I haven't even used the second one. Now let's use the second one. So I take two odd indices and suppose that x sub 1 is a Fibonacci number, x sub n1, and x sub n2 is another Fibonacci number. So we have two relations, and we are mathematicians. When we have two relations, we do two equalities, we do whatever we want with them. We can multiply them, we can add them, we can exponentiate them. We decided to do a less orthodox operation, which is let's take the GCD of them. Well, it turns out that the GCD of two such numbers has a meaning in the world of Fibonacci numbers. The GCD of two Fibonacci numbers is f of the GCD of the indices. And it turns out that if you look at the x coordinates of Pell equations for n odd, then the GCD of xn1 with xn2 for n1 and n2 that's odd, it also has the same meaning, namely is x of the GCD of n1 and 2. These are properties more general to things called Luka sequences. So in some sense, what it says that if I already have two solutions, then I get another solution by taking the GCD of them. Of course, this new solution that I get, it might have been one of the previous ones. For example, if n1 divides n2 and m1 divides m2, then I don't really get a new solution because I take the GCD of two numbers that divide each other, which means that it's the smallest of the two numbers. But in this way, I can kind of play around with the d, modify it, change the name of x sub GCD of n1 xd by x1. So I can assume that one of the Fibonacci numbers is actually the beginning one, the first solution. And then the next one is some other solution. X sub n is alpha to the n plus beta to the n over 2, where n is odd. And this number, the index of this Fibonacci number is m1t, is divisible by m1. And it turns out one can show that from these relations, one can show that n is bigger than t. So you have to grow faster in that side than in that side. And from now on, the argument has an analytic part and an arithmetic part. The analytic part, write the Fibonacci numbers with their Binet formulas, which is like a linear combination of golden section to M1 and the reciprocals of the golden section to M1, both here and there, and take the difference between leading terms in both sides. So the leading term here is alpha over 2 because beta is subunitary. It's like 1 over alpha. And the leading term there is going to be the golden section to the power M1 over root 5. So put the big terms in one side and put the small terms in the other side. This is what we do when we solve exponential Diophantine equations. So this inequality comes from the first equation by taking the two leading terms and putting them together on the left. And this one comes in the same way from the second relation. So I have these two relations in here. So what I can do, when you do linear forms in logs, what you can say, you say, well, let's prove that this one is non-zero. You do some argument and you prove that it isn't, because if it would be, then root 5 over 2 should be an algebraic integer because alpha and gamma are units. And then you say, okay, I take the part from here and I compare it with the lower bound that comes on the left-hand side, which comes from linear forms in logs and so on. And I get an inequality that says that M1t is roughly at most the log of M1t times log gamma, which is known, times log root 5 over 2, which is known, times log alpha. The problem is that alpha is not known because alpha is x1 plus root dy1 and you don't know who alpha is. But this is why you have two equations. What we did at that time was to do an arithmetic part. The arithmetic part was very interesting. What we did, we took the same two relations and we divided it against each other. It turns out that x1 divides xn. In fact, xn is a polynomial in x1, which has 0 as a root. This is why x1 divides xn. And if you look at the next term, which would be xn over x1, has a certain value modulo x1, which is n. And you can play the same game here. The ratio of f sub m1t over f sub m1, it has, you can write down some residual class for that one in terms modulo fm1. And if you go to these relations, xn over x1 is plus minus 1 mod x1, fm1t over fm1 square is plus minus t square modulo fm1. Those two numbers are the same. those two, well, the square of that one is the same. Therefore, the square of that one should be the same modulo x1. You have to prove that n and t are essentially different, because otherwise you take the difference between n squared and t squared and it could be the number 0. But you prove that this number is non-zero. Since it is non-zero, you get some relation in here saying that f sub m1 is a divisor of this non-zero number and n is bigger than t. And because of that, this gives you a very low bound on m1, because if m1 is exponential in the parameter m1, it's like the golden section to m1 divided by √5. So this tells you that the golden section to m1 is at most 6 times n squared. And because of that, m1 is logarithmic in n. Once you have that m1 is logarithmic in n, then you're basically done, because what you do, since m1 is logarithmic in n, you go over here and you say that alpha that came out of the power m1 is about alpha, which means that m1 is about log alpha. But we said that m1 is logarithmic in n, so log alpha is logarithmic in n. So the problem that you had when you were trying to apply the Baker bound here, where it was giving you that m1 is at most the log of m1t times the log of alpha, has disappeared now, because the log of alpha is at most log of n. So this gives you that n is at most log of n, and this gives you bound on n. And then you go and you put your numbers in there. You get n is 7 times 10 to the 14. M1 is at most 145 if you go to this inequality, and the rest is just calculation. And you can see how this method will also work for x squared minus dy squared equal plus minus 4. So the question was, were we on to something or not? Or was it just some hocus pocus, we were lucky because of certain arithmetic properties that the Fibonacci sequence had? Well, it turns out that it also works with the rep digits. Let's do the same program. X squared minus dy squared equal to 1. Xn equal a times 10 to the m minus 1. Let's do the rep digit now, and let's try to mimic the previous argument. Suppose that n is even. Then I know that the left-hand side is 2x squared minus 1, like in the Fibonacci case. The right-hand side, now I don't have a Pell equation to stick it into like I had with the Fibonacci number. But this one is pretty clearly a polynomial in 10. Well, m is not fixed, so you can't pretend that it's a polynomial in the value 10, because the degree is not fixed. But you can put m in the residual classes modulo any small number you want. For example, you can take the small number 3, and then m could be a multiple of 3, or a multiple of 3 plus 1, or a multiple of 3 plus 2. Therefore, this number over here, it's either a cube minus 1 over 9, or 10 times a cube minus 1 over 9, or 100 times a cube minus 1 over 9. And a is also fixed. So if you look at this guy, now you notice again an elliptic curve like before, because here you have some square, and here you have a polynomial degree 3. The argument is not going to work for the digit a equal to 9, because when a is equal to 9, this 9 cancels with that 9, this negative 1 cancels with that negative 1, and you don't really get a square equal a polynomial that has only simple roots. You get something else. But actually, when a is equal to 1, this side just becomes, you're asking yourself is if 10 to the m can be twice times the square. And it can't be, because either m is even, which means 10 to the m is the square, or m is odd, which means 10 to the m is 10 times the square, but certainly is not 2 times the square. So the integer points, we had that part. So now suppose that n1 and n2 are odd, and I have xn1 is a rep digit, xn2 is a rep digit. So let's do the GCD game. When I do the GCD game, funny enough, the GCD of 2 rep units is a rep unit, 2 rep digits is a rep digit. You probably don't believe me, and in fact you shouldn't, because it isn't. But in some sense it is. You just have to lie. You have to lie, and you have to pretend that 21 is a digit and that 63 is a digit. If you lie like that, then it turns out that the GCD of 2 rep digits is always a digit, a rep digit, except that the digit could be 21 and 63. Once you've seen something like that, you probably can prove it. And the way you prove it, you look at the GCD of 10 to the m minus 1 over 9 and 10 to the m 2 minus 1 over 9, and that's the number over here. And then you have a1, a2, and you can take some GCD of them. But what sometimes happens, where do you get, for example, 21? It sometimes happens, for example, that both m1 and m2 are multiples of 3. And then when you divide m1 by the GCD of m1, m2, and m2 by the GCD of m1 and m2, one of them can still be a multiple of 3. Not both of them, because you have already simplified the GCD, but one of them can still be a multiple of 3. if you do that and one of them is still a multiple of 3, then the quotient of that number to that number, it's a multiple of 3. And it could be that there is a 3 sitting in here that hasn't been picked up by the GCD of A1, A2. That 3 is going to come in and it's going to contribute to that 21. So here are some numerical examples. Okay, take the GCD of these 6 3s with these 7 7s. You compute it, it's 2331. It ends up being 21 times 111. Take the GCD of these 6 9s with these 18 7s. It's 63 times 111. So this can, and this is the only thing that happens. And this actually works even for general bases. The GCD of 2 rep digits in general base is basically a rep digit, except that the digit that you get some exceptions like here 21 and 63, but they are no larger than the square of the base that you started with. Okay, so now you do the same analytic argument. You get that M1 is, these numbers have the same properties. So in some sense, you may assume that one of them is 1 and the other one is x sub n and n is odd. Then you take xn over x1. This has some residue class modulo x1, which is n. Then you take the quotient of these two numbers. You can forget about the a's and the b's because they give you some rational number from a finite set because A has at most these values and B has at most these values. But when you take the 10 to the m1 over t minus 1 and you divide it by 10 to the m1 minus 1, you get a polynomial in 10 to the m1, which is the same as a polynomial in 10 to the m1 minus 1. And it turns out that this is congruent to m1 modulo 10 to the m1 minus 1. So again, you get some congruence argument, identical like in the Fibonacci case. And you can say, therefore, that M1 is at most logarithmic in N. And then, therefore, alpha is at most logarithmic in N. Then you go to a linear form in logarithms, you get N is at most logarithmic in N, and you bound N. And this is what was used when I mentioned the result with Bernadette Fay. I mentioned this result over here. This result is just some off-the-shelf result that comes from Baker's theory. What Baker did, he has one of his applications of his linear forms in logs is that if you have one of these super elliptic equations, you have a square in this side and you have a polynomial on the right, which has only simple roots and of degree at least 3, then this equation has only finitely many integer solutions, and Baker is able to write down a bound, which is double exponential in the height of this polynomial. And because of this bound, we can get these results. But this result, as I said, it's impractical, and it came up exactly from applying Baker's theory for the case when n was even. Okay, so we have that. Then we said, what about the Fibonacci sequence? We can start with the Fibonacci sequence, which satisfies the third order recurrence. Each term is the sum of the previous 3 terms. It starts with some values, 1, 1, and 2. And then I was being visited in South Africa by Amanda Montejano, Laszlo Sala, and Alain Togbe, and we decided to work with this problem. What about x coordinates of Pell equations being Fibonacci numbers and being at least 2 of them? And then this equation again has at most 1 solution, except when the d equal to 3 and d equal to 2. And in these cases, you get a few extra solutions. And here's the 4 of us working on Fibonacci numbers. Shanta might recognize this place. It's a game farm close to my game farm in South Africa. We call ourselves the Alpha Team, from Amanda, Laszlo, Florian, and Alain. And I'll let you guess who is who. You see, we weren't wearing masks then because it wasn't COVID time, but we were wearing goggles and helmets. It's very difficult to work on these Pell equations. Well, the problem is different from the previous ones because the 2 elements that we had in there both failed. One of the elements was the analysis of, let's say, a member of the Fibonacci sequences of the form 2x squared minus 1, which worked well for Fibonacci numbers of this shape or rep units of this shape. Here it doesn't work. Also, we have no idea how to relate the GCD of two Fibonacci numbers with members of the Fibonacci sequence itself, like we did with Fibonacci numbers or red digits. So we needed to do something else. It turns out that when you need to do something else, you have to go back to the basics. Maybe what we were doing, it was a bit too fancy, and that's why we couldn't apply it to more general situations. So let's take again the golden section and its conjugate. Let's take alpha, the element that gives you the initial solution of the Pell equation. Beta is plus minus alpha to the minus 1, depending on whether the minimal solution had a negative 1 or a positive 1 in the right-hand side. So then the equation xn equal fm can be written in this way. This is the nth term of the Pell equation, and this is the mth term of the Fibonacci sequence. As we did in the past, let's group main terms in one side and the other terms in the other side. The main terms here are alpha to the n divided by 2, and here is gamma to the n divided by √5. And we put the other things in the other side, and they have exponential decay. They are really, really small. This means that alpha to the n over 2 is very close to gamma to the m over √5, which you can rephrase by saying that the element alpha to the n multiplied by 2 over √5 multiplied by gamma to the negative m is very close to the number 1. And when you have a product close to 1, what you do, you take the logarithms of that product and you get a sum which is close to 0. This sum is going to be a sum of logarithms. This guy is the log of alpha to the n. This guy is the log of 2 divided by √5. And this guy is the logarithm of gamma to the m. And maybe I made some mistake with the sign here. I think I made a mistake. This should be the plus sign, but it doesn't matter. It's not going to induce much of a difference. So I have this guy in here, which is small now. And as I said, linear forms, what will give you, for example, if you look at gamma to the m, what you want to bound m. M is the largest of the parameter, this one. Because if you bound m, you have bounded the mth Fibonacci number. And then once you have bounded the mth Fibonacci number, xn is n is at most m, xn is some known polynomial in x1, and you try to find all the instances and you solve it. So when you go to linear forms in logs, it's going to tell you that m is at most log of alpha times log of m. And again, the problem is that log of alpha is not known. But you have another equation. You have two of them. That is, you have an equation for x sub n equal fm, but you have x sub n prime fm prime. So you get another relation like this. Now pretend that they are actual equations. So pretend that this O, it's actually not O is 0, and wipe out everything from there. Then what you have two linear equations. In the variables, I don't know, you can call them maybe log alpha and this one and that one, log of 2 √5 and log of gamma, let's say. So, and when I have two linear equations, if I have a variable that bothers me, then I can eliminate it by multiplying each equation with some coefficient and taking the difference. That's exactly what we do here. I multiply this guy with the number n, and I multiply the previous one with I multiply the previous one with the number n prime, and I take the difference. And when I take the difference, I get this form, which is small. I guess not with n and n prime. I guess it was, oh, I see. This number should have been the number gamma. I'm sorry for that. It should be n prime m minus m prime n log gamma. So multiply this one by n and the previous one by n prime. Eliminate alpha, which is the one that you don't know. And you're going to get a linear form in log of gamma in log of 2 √5. And now those things are known, because now here you just get the known number gamma, and therefore you're going to get that m is at most the logarithm of m prime when you do linear forms in logs. But m was also at least the log of alpha, which means that the log of alpha is at most the log of m prime. Thus m prime is at most the log of alpha times the log of m prime, which is log of m prime squared. How was that? That was very easy. And we bypassed all these GCD arguments and congruences and so on. So actually this approach was very useful. Let's see how useful it was. For example, it worked with a set of numbers which can be written as a sum of two Fibonacci numbers. So instead of just working with a set of Fibonacci numbers, look at the set of numbers which are sums of two Fibonacci numbers. These ones are a bit bigger. Then this equation has at most one solution. There is, for every d, there's at most one x participating in the Pell equation, x squared minus dy squared equal plus minus 1, which is a sum of two Fibonacci numbers, except for d is equal to 2, 3, 5, 11, and 30. Is it true that we can extend this one? We don't know if it is true. The problem with those things is that as you try to extend them, as everybody that has played a little bit with linear forms in logarithms knows, one of the problems when you try to apply linear forms in logs is that you have to prove that the lower bound that comes from Baker's method that you're trying to use in that linear form, the linear form is not zero. And once you have too many Fibonacci numbers in there, then as you keep on going along, you hit all these linear forms, and it being zero, it results in some nasty differential equations which you cannot prove, you cannot solve, and this is why. But for example, if I replace a sum of k Fibonacci numbers by, let's say, a sum of k1s, then probably the answer is no. And why is the answer no? Because the reason is, let's take a Pell equation which has a -1 in the other side. For example, x squared minus 5y squared equal -1. It has a solution. And let's look at the third solution of that. And at the second solution of that, the second solution ends up being twice times the square of the first solution plus 1. Well, if the first solution was a power of 2, then this becomes a power of 2 plus 1, which is a number that is a sum of 2 powers of 2. So that already you can see that you have parametric families like that, which are sums of 2 powers of 2. And you can go further. For example, the third solution, it's 4x1 cubed plus 3x1. Make again x1 to be a power of 2. Then you get 4 times the power of 2 plus 3 times another power of 2. And then 3 times another power of 2 is a power of 2 plus the smaller power of 2. So already you get numbers which have, when you write them in binary digits, you have 3 1s in them and you have infinitely many d's. So there the problem is difficult. We don't know how to do it. And this is my co-author, Carlos Alexis Gomez Ruiz. He was my PhD student at the time. Now he's a professor in Cali, Colombia. We also did it with products of two Fibonacci numbers. And here's the result. If you take the set, which are products of two Fibonacci numbers, then for every d, there's at most one x participating in the Pell equation, which is a product of two Fibonacci numbers, except when d is equal to 2, 3, and 5. You can also do it with generalized k Fibonacci numbers. So instead of stopping at the Fibonacci sequence, you can keep on going. Take any k greater or equal to 2, take the recurrence such that every term is the sum of the previous k terms. You have to make some decision about what the first k term should be. And the decision usually is made, a problem that has been studied by people is to take k minus 1 consecutive zeros followed by a 1. And you can shift the problem in such a way that all the zeros are in the past, including the moment 0, and 1 is f sub 1. And with this convention, then f sub 2 is equal to 1, f sub 3 is equal to 2. Now, if it's Fibonacci number, f sub 4 is equal to 4. If it's just a Fibonacci sequence, then f sub 4 is equal to 3, because you have stopped adding those powers of 2, and so on. And the question is, can we generalize the Fibonacci result? And we generalized it together with my PhD student, Mahadi Damuliran. We took k to be any fixed integer. We took the Pell equation, x squared minus dy squared equal plus minus 1. And we looked at two values of x's being in the kth generalized Fibonacci sequence for two different solutions, and one bigger than n2. It turns out that you only get solutions at small indices. So for example, if n1 is equal to 1 and n2 is equal to 1, and you get some choices for m1 and m2, or if n1 is equal to 1 and n2 equal to 3, and you get some other choices. Now, instead of bothering you with the terrible details of that, you can see already that these things are pretty nasty. You may wonder, how did we find them? Well, it turns out, So in general, those numbers that grow very fast, like x coordinates of Pell equation and Fibonacci numbers, they don't, K Fibonacci numbers, they don't meet unless there is an algebraic reason for them to meet. And here's the algebraic reason. If you look at this K generalized Fibonacci sequence, it turns out that at the beginning they are powers of 2. They keep on being powers of 2 for n equal 2 up to K plus 1. Once it gets to K plus 1, it starts changing. So the K plus second term, it's the powers of 2 that you expect it to have, but then you subtract 1 from it. Then if you go one step further, you subtract 3 from it. And there's some formula of how much you have to subtract from it. Actually, there's a formula of Curtis Cooper and Rob Kennedy, which tells you basically for every finite interval between K plus 1 times I and 2K plus 1 times I, so between I, K plus 1 and I plus 1 times K plus 1, it gives you some complicated formula with binomial coefficients. But for our purpose, we only needed it in, let's say, the second interval. Now, how did we match things up? Well, let's also look at the Pell equation and the x coordinates of Pell equations. For example, x2 is related to x1 in this way. x2 is 2x squared minus 1. And x3 is related to x1 in this way. x3 is 4x cubed minus 3x. So then what we said, let's suppose that this one is x1, and let's suppose that this one is x2 or x3. So I have to match this number with that number. When can I do that? For example, here take n minus k is equal to 2. Then n minus k is equal to 2. The exponent here is 2 minus 3, which is negative 1. So 2 to the negative 1 is 1/2. It multiplies the 2, and it becomes this 1 in here. So if you make n minus k is equal to 2, and then you take an n such that n is odd, then 2 to the n minus 2 is 2x squared for some x. So you got this one. Now to get this one is a bit trickier, because now you want, first of all, n minus 2 to be 2 mod 3 in order for this x that comes from here to be an integer. So you want to match 4x cubes with 2 to the n minus 2. That gives you some value for x. And then you go into here and you say, with that value of x, ask of 3x to be n minus k times 2 to the n minus k minus 3. And it gives you some parametric families in n and k's, which are a bit terrible. So this one is the family that comes, and you can kind of see why this one is a bit easier and this one is a bit more complicated, because it's more complicated to match this one. And interestingly enough, there are no other solutions at all, even sporadic ones, which we found it fascinating. This is Mahadi Damgira. I saw him at the talk. All right, with factorials, this is the result that we obtained when Shanta visited me in December of 2018. Which I wanted to play the same game. Can x sub n be a factorial in 2 different ways? Well, it turns out that there we could do much better. We could say that if x sub n is a factorial, then n is equal to 1. And here's a picture of, this is Mark, my PhD student, and this is Shanta proving this theorem, and this is myself. This is done in my office at WITS. So let me take a little detour through Luka sequences. I take co-prime integers R and S, such that this equation has 2 roots. I eliminate some equations like x squared plus x plus 1, for example, which has cubic roots of unity and so on. Those ones I don't like. So I eliminate cubic roots of unity and roots of unity of order 6. Let alpha and beta be the 2 roots with alpha greater or equal beta in absolute value. Then the amount alpha to the n minus beta to the n over alpha minus beta is called Luka sequence of first kind associated to that, and alpha to the n plus beta to the n is called the Luka sequence of the second kind. Alternatively, you can define them by saying that the u starts at 0, 1, and the v starts at 2r, where r is the sum of those roots, and then they follow this recurrence relation that's given by this quadratic equation. Now, it turns out I wrote a paper a long time ago with Pantes Stanica. I understand he also visited Delhi at some point, where we proved this. One thing that I like about that paper is that it has no word in the title. The title of the paper is just this formula. And what this formula means that it is the largest solution of a product of distinct Fibonacci numbers equal a product of factorials which don't necessarily need to be distinct. And by largest solution, I mean the solution for which the value of the left or right-hand side, which are equal, is the largest possible among all solutions. You have to make them unequal somewhere in the left or in the right, because if you allow equalities, then you just take a relation like this and you square it, and you get another relation like that. The product of some Fibonacci numbers equal a product of some factorial. Now, take products of factorials. Let's call this set P of F. Then one can prove easily that the absolute value of un being a product of factorial has only finitely many solutions n. In fact, let me prove it here on this line. Suppose that un is a product of factorial, and suppose that mk is the biggest factorial. Then the left-hand side is exponentially in n, is at most 2 times the absolute value of alpha to the n, where alpha is the biggest, is the root of the largest absolute value. They might be equal if they are complex conjugates. Now, there is a fascinating theorem by Bilouan, Rowe, and Voutier, which is crowning some theorems that started with Birkhoff and Van Diver and Zygmundi and Carmichael at the end of the 18th century and early 19th century, where they proved that if n is sufficiently large in an absolute way, in this case is 31, there is a prime factor that divides the left-hand side, which has the property that it's called primitive. It has several properties, but one of the properties is that it's at least as large as n minus 1, and that's an important property for us. This prime has to be observed by these factorials. So in particular, it has to be detected by the largest factorial. So mk has to be at least n minus 1. And now you use Stirling's formula that says that mk is at least n minus 1. And therefore, mk factorial should be at least n minus 1 over e to the power n minus 1. Now look at this left-hand side and look at this right-hand side. This left-hand side goes to infinity much faster than this one. So this gives you a bound on n. The problem with this bound on n is that it depends on the parameter alpha. And I had the idea that maybe if un is a product of factorials, then n should be bounded absolutely. So I had some notes there, and I had these huge bounds. So I invited Shanta to come and visit me in South Africa and help me and my student lowering these bounds. And he was kind enough, and he came. And after several revisions, the paper has been published recently in Monatshefte für Mathematik. Here is where we got to. The general equation, un is a product of factorial, implies n is at most 62,000. If additionally the roots are real, then n is at most 12. In the case of the x-coordinates of Pell equations, then the x-coordinate of Pell equation is really this sequence, alpha to the n over beta to the n. You have to divide the number 2, but then you can put the number 2 in the right-hand side, and 2 is 2 factorial, so it's the same thing, really. So because of that, we could, as a byproduct of our argument, is that if the x-coordinate of a Pell equation is a product of factorials, is a factorial, then n is equal to 1. If it is a product of factorials, and if the Pell equation has plus minus 4 in that side, we get a few sporadic solutions. And one of the interesting things that was in that paper computationally was a recent result of Bennett, Martin, O'Brien, and Rechnitzer about prime numbers in arithmetic progressions with small moduli. They have very explicit bounds. When people work with explicit prime number theory, they work with, let's say, a paper of Rosser and Schoenfeld of the 60s for estimates, explicit estimates for primes. And of course, there are a few better versions by Dussart and so on. But even for most practical applications, those bounds are not. But it turns out that in order to work with those things, you would also like to have bounds of a comparable quality for, let's say, primes which are 1 mod 3 or 3 mod 4 or whatever. And this paper does exactly that. It does it for small progression. It has very nice estimates. It's a huge paper. It has 100 pages, but it's very useful. Okay, now let me go back to, this is a review of that paper that I wrote with Apollinaire. And let's look at this paragraph. The paragraph says that our proof about x-coordinates of Pell equations in which are rep digits, the proof breaks the problem into several cases which require a wide range of techniques to analyze, including analysis of elliptic curves and linear forms in logarithms. The techniques appear to be specific to the base 10 case, so generalized to other bases would require a separate work of equal magnitude. Now, as I said, with Bernadette Fay, we had some theorem about other bases, but we had d smaller than x of 10b to the power 10 to the fifth, which was impractical. So in some sense, Joe was correct, but it kept on bothering me that maybe we should actually have some linear algorithm that does it for all bases. And we did it. So I invoked one of my recent PhD student, Faith Zotor. And here's what we did. Let b be an integer greater or equal to 2. Look at x coordinates, which are 2x coordinates, which are base b digits. Then the max of all the 4 variables is at most 6 times 10 to the 27 times log 2b to the 6. And this you can actually use in computations. So this is a paper that just appeared in Research in Number Theory. Now, let me tell you where one of the hurdles that then we have a numerical corollary. Take b from 2 to 100. All positive integer solutions have at the largest n is at most 5. And all the d's are in this list. I'm not going to give you the list of all the possibilities. What I'm going to tell you is that the d's are in this list. For every d in this list, generate the minimal solution of your Pell equation. Compute the first 5 ones in each case. And of those set of numbers, write them in base b, where b is any integer between 2 and 100. And whenever you're going to find coincidences, that's all the coincidences that you're going to have. So in some sense, I'm giving you enough information to recover everything you need to know. And this is my student Faith. He's originally from Ghana. Now the problem was a bit harder, and let me tell you why the problem was harder. So you write down your 2 relations, you eliminate the variable alpha, which you don't know what it is, and you get this linear form in here. Well, when you do linear form in logarithms, then I'm going to finish in 2 minutes. When you do linear form in logarithms, then you want to know that this linear form is non-zero. But so your best bet would be that log b, log 2a1 over b minus 1, and log 2a2 over b minus 1 are linearly independent over q. Well, but it turns out that they are not always. For example, a1 could be equal to a2, in which case these 2 logs are equal. Or 2a1 could be b minus 1 if b is odd, and then this log is equal to 0. Or b is a power of 2, and 1 of a1, a2 is b minus 1. In this case, this is just log 2, and this is log of a power of 2. In addition to that, there is 788 other triples for which the Q span of this is 2. And here's some terrible ones. For example, write b as b1 to some power, the best you can. And then write 2a1 over b minus 1, b1 to the y1 times some other number, and 2a2 over b1 minus 1, b1 to the y2 to some other number. And here's some crazy examples that you get. You don't even think you're going to get numbers that have 13 digits in there. I mean, you just go up to 100 digits. Then you even get numbers that are not even rational. You get things like that. So we actually had to go through all these examples and to check that things work. Okay, I wanted to say something else about Pell's equation, but maybe I'm running a little bit out of time. The idea was that there's a problem of Pell which addresses a representation of a number c as a difference between a to the x minus b to the y, where a and b are known and x and y are not known. And he proved that basically if c is large enough, then x and y is uniquely determined. And you can change a to the x and b to the y by 2 recurrent sequences, and you can ask the same question. And if you ask the same question and you change one of the sequences to the sequence of x coordinates of a Pell equation, whatever Pell equation you want, and the other sequence is the powers of 2, then it turns out that you always have at most 2 representations, except for this crazy number. For example, if d is equal to 2, then the number -1 is represented in 3 different ways. There's a difference between an x and the power of 2. And actually this result is 2 papers. In one paper, we proved that there is no number which has 4 representations. And that paper appeared in GNT last year. There are infinitely many numbers which have 2 representations. There are infinitely many d's. And for each d, there's at least one c, which has infinitely many representations, which has at least 2 representations. There's a difference between an x sub n and the power of 2. And there is only this example. But this paper has been submitted and hasn't been accepted yet. My hope is that the referee is in the room and understands how beautiful it is. And when I finish my talk, I already get an acceptance of that paper. And then, and this is Harold Eraso. He was a student of Carlos Alexis Gomez, which is also a member of this project. But he was an undergraduate student. Now he's a PhD student at IMPA in Brazil. So he was an undergraduate student in Colombia, and he worked on these questions. And we have some things about y coordinates. For y coordinates, the answer is different because you have parametric families in which you can have Pell equations, you have infinitely many Ds for which in binary recurrent sequences, you can have two values of the y which live in that binary recurrent sequence. Here are some examples. For example, for d equal 2 to the 2 to the L minus 1, then both the first coordinate, which is 1, and the third coordinate, which is 2 to the 2L plus 2 minus 1, live in the sequence 2 to the N minus 1. But our result is that if you take any binary recurrent sequence, then there are only finite many Ds for which you find 3 values of the y in there. So 2 values of the y you can find parametrically, even for Fibonacci numbers and so on. There are infinitely many examples of Ds for which the y coordinate admits 2 Fibonacci numbers in there. But we don't know about the Ds for which there are 3 Fibonacci numbers in there. That's a project that Faith is working with. And that's it. Thank you.
Thank you, Professor Luca. Professor Ajit Iqbal Singh wants to ask some questions. Ma'am, you can unmute your audio and.
Yes, wonderful talk. I thoroughly enjoyed it. Now, you took, XN as nth Fibonacci number. And yes. What about YNs and what about Luca's numbers?
Yeah, exactly. That's what I mentioned on the last slide. For about the YNs, the result that we have over here is that for every binary recurrent sequence,
okay,
you have only finitely many Fibonacci, you have only finitely many Ds for which you find 3 Ys, which are members of that sequence. But we haven't worked out the Y equal the specific Fibonacci sequence or the specific Luka sequence. That we haven't done yet. This is just the general result, but a general result, you know how it goes. You have some constants in there, and then if you actually want to compute and follow the general methodology, you might not succeed because the computations are too big. So for particular cases, you have to be a bit clever sometimes. So we haven't done the specific Fibonacci and Luka sequences in that case.
Thank you, because these Fibonacci and Luca's numbers and which in simpler language is equiangular lines. The dimension D in C raised to D complex Euclidean space. For certain Luca's numbers dimension D, these symmetric informationally complete positive operator valued measures, SIG POVM as they are called in short, exist. That is equiangular lines exist. And this work is by Grassel and Scott. And they conjecture that it will be okay for all. So these things will be related to their work. And I have an elementary article on the topic on archive with Shiva Kumar and Chatterjee. And, it is 1804.08100. And also, these Fibonacci numbers occur in resonance valence bond states, nearest neighbor covering. So they occur at many places, but I'm telling 2 places which people here at ISI are familiar with through Professor Parthasarthi being there and giving such things too. And I would be interested in further progress, and I would like to send your talk to Grassel and Scott.
All right, sure.
Okay, thank you. And maybe Shanta can ask Grassel and Scott to give a talk. And then Professor Lucas can join, and then they can converse also. This is very interesting, very interesting.
Thank you.
And another thing is about reciprocals of Fibonacci numbers. They occur in interval filling sequences, paper by Paul Ribbenbaum in Ensine Math 1985, old one. Interval filling sequences, sums of the reciprocals. So I don't know how the solutions of Pell's equation can enter interval filling sequences, because reciprocals of Fibonacci do enter.
I see.
So I would be interested in that, because there are factor measures where this is used for atomic measures.
Yeah, well, I'll have to look at that paper and see if these X coordinates share some properties. I don't know. Thank you.
I mean, how the reciprocals enter can be seen in my paper with Lalton Puya in Journal Convex Analysis 2008. They were defined by Kakaya, interval filling sequences. Thank you.
Thank you.
Any other questions?
So yeah, Florian. Okay, nice knowledge. So by the way, this result with phi, your last results. So is it also based on linear forms in logarithms, or?
Yes, it's also based on linear forms in logarithms, but it's the problem is more complicated because you see, once you have an x of a Pell equation, that already determines basically everything because somebody gives you the x, then you compute x squared plus minus 1, and the d sits in there. Once the d sits in there, so does the y1 and so on. But if somebody gives you the y, then that y already comes equipped with infinitely many d's, because that y you're looking at, then you only know y. So dy squared equal x squared minus 1. This means that d should be x squared minus 1 over y squared. Even though y is known, x can be any integer such that x squared minus 1 is a multiple of y squared. So there's infinitely many of them. So to me, this is why the problem is complicated, and it's basically one step harder, because somehow you need at least two relations in order to get your hands on it. And then starting with the third relation, then you can eliminate some of the variables. So for example, if you start with any sequence that contains one and an infinite many even numbers, then there's going to be infinitely many d's with the property that there's at least two y's in that sequence. So this is why, but yes, it's based on linear forms in logarithms.
Okay, thank you.
Any more? So let's unmute our audio and thank Professor Luca again. So thank you.
Yeah, you see, you took sums of k previous numbers instead of just 2,
Yes.
and there are Padovan numbers.
Yes, but those Padovan numbers.
Where you missed just the previous one, but take into account the previous to that. So
yes, Padovan numbers.
Yes.
My student Mahadi Damulira, who's in this audience, he studied these Padovan numbers in exactly the same way. Like he asked, I don't know if it was you Mahadi that did maybe two x coordinates being Padovan numbers or sums of two Padovan numbers. So there are some people, some colleagues that are working on that. And also a former student of mine from Mexico called Santos Hernandez. He also had some papers on that. So yes, some people looked at Padovan numbers. They are a bit like Fibonacci numbers. Just the characteristic polynomial is a bit different. But it has the same sort of structure, like it has one root in the interval 1, 2, the other two are complex conjugates, the product of the roots is 1, so most of the ingredients are there for them to work.
So anyone wants to say anything? Chat? So I can close the session now?
Yeah, we can. Yeah, thank you.
All right.
Thanks.
Well, thank you again.
Thank you.
Bye.
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 Yeah.